We got a man standing on a wall, and he throws a small ball vertically upward with a velocity of 5.6 meters per second. The ball leaves his hand when it is a height of 3.1. All of this is just shown on the picture. I do not recommend wasting time on this exam. You get an hour and 15 minutes. So you don't want to spend a lot of time reading what is already in the picture. Show that the ball reaches a maximum height of 4.7 meters. You have an option of doing either energy or kinematics for this problem. I think that energy is easier, but you guys, for some reason, think kinematics is easier, so I'm going to start with kinematics or energy. I'm going to start with energy because that's the one I know immediately what to do. Right now, we got MGH. We got potential. And we just added some kinetic, 1/2 mv squared. And then as this ball goes up, eventually it is no longer going to have any kinetic energy. Once it gets to the max height, it'll only have potential energy. So this is going to equal mgh final. And we just solve for mgh final. All the masses cancel, which is really good news because they didn't give us the mass of the ball. And we would have gravity, 9.81 times 3.1. Plus 1/2. The v, which was 5.6 squared, would equal 9.81 times h final. And you just solve for h final, and you get your answer. And the answer is 4.7 meters for h final. When you solve that, it does say show, but I'm trying to save a little bit of paper because I think that you might want to do the kinematic version as well. All right, the kinematic version would be, I'm going to do it over here, you would have v final squared is equal to v initial squared plus 2a. They don't use delta x or delta y, they use s. And actually, they don't use v final and v initial, they use v and u for v initial on the actual formulas, the international formulas. The final at the top is still going to be 0 because we want it to be at that apex moment where the final is 0. The initial is 5.6 squared. To negative 9.81, and then you solve for s. The difference is when you solve for s here, you end up with 1.6, but then you have to add the 3.1 to get to the 4.7 meters either way. So both of which are fine, and answer key used kinematics if it makes you feel better. Okay? The man does not catch the ball when it falls, so he's very unathletic. Calculate the time for the ball to fall from its maximum height to the ground. So read carefully. Also recognize that even if you can't do part A, for any of the ones that say show, you can almost always do the next part because you use the answer. It's at a height of 4.7. It is falling to the ground. So it is going to go down by 4.7. That would be our delta y, would equal VIT plus 1/2 AT squared. You get that formula, but they're going to use S and U and different variables. The initial speed is not 5.6 because it is at the max height. At that time, it has 0 speed. You can still plug in the t, but it's going to end up equaling 0. Plus 1/2 negative 9.81 times t squared. If you mix up the negative part, odds are you're going to catch it because you'll be like, I'm square rooting a negative, and that won't work. And then you just solve. We got 4.7, not a 7. 4.7 is equal to negative 4.9 t squared, and it's negative 4.7. You divide, you square root, and you get a time. You don't need to write time. You get time of 0.98 seconds. For sig figs, a lot of people are asking for sig figs on this. Don't overthink the sig figs. Almost every single question has been rounded to 2 sig figs, so almost all of your answers should be rounded to 2 sig figs. And you can know how many sig figs by looking at all the raw data, just like we did for the lab. 3.1 meters, 2 sig figs. 5.6 seconds, 2 sig figs. Figure 3.1, even 2 sig figs, but that has nothing to do with it. All right. This is the part I haven't looked at. The ball leaves the man's hands at a time of t equals 0 and hits the ground at a time as t is equal to t, bigger t. All right. On the figure, sketch the graph of the variation of the velocity of the ball with a time from a time to here to here. So Numerical values for V and T are not required, so we do not need to write the actual numerical values. We might use them later on, but we don't need it. We do need to think in terms of like how long is this going to take to go up versus come back down to the ground. So that part I do think matters. I think that this T is also in the wrong location, but I could be wrong. Let's make sure. Time T is equal to 0. Okay, so it starts when it leaves his hands, and here is where it hits the ground. And then we're going to have a little bit of graph that is not going to be doing much. So what is the velocity in the beginning? Positive or negative? Well, it was going up at 5.7. We didn't have to write that, but if we wanted to represent this as 5.7, we could. It was positive in the beginning. And then it's going to slow down as we go forward. Hello.
It says big T for the graph, which is the one all the way on the right. I think it's just saying that that's the like scale, like it's time for the x-axis.
Time for the x-axis, yes. And then the little t right here is when it hits the ground.
No, it says big T.
Big T.
And little t showing you that axis is time.
All right. So this is the ground?
Yeah.
Yeah.
Well, that I want to do little t as the ground. I'm going to do both. Actually, I think I'm going to do little t as the ground because it's more educational, even though it's wrong. Yeah. I'm not good at reading, just so everybody knows. When you move to AP, reading is more important, and you're going to have to help me. So as it leaves, it's going to slow down, and once it reaches the point where it's at its max height, that is going to be right here. I'm going to just assume it's right there, mostly because it's a thicker line, and it's going to go down, and it's going to always have the same slope, okay? And I am going to definitely get this wrong because I ran out of graph, and I'm in pen, so I'm not going to redo it. So this, I'm going to say right here, big T is when it hits the ground. I'm getting it wrong. Don't do what I do, okay? Big T is when it hits the ground. It will have a constant slope of that, and not only that, but it should be less time here and more time here. Why? Because it was going, like when we had the guy throwing it, it only went up a very short distance relative to how far it had to fall back down. So it would spend more time falling than going back up type of thing. Okay? Not only that, but when it went up, it also had to go back down. This time would be the same as that time, how long it took to get up to the max height. That time it took up to get to the max height would be the same time it takes to get back to his hands. And then it has to fall further. Okay, but no matter what, the slope should be consistent because the slope is going to be gravity, negative 9.81. Once it hits the ground, this is the teaching moment that I wanted, then the velocity would be 0, which would not be a part of the answer, but that's where I wanted to like teach you something in case they have something like that. In reality, the actual graph would probably look more like something like this. This would be probably the actual answer like that, where you spend more time below than above. That looks ugly. Oh well, it's in pen. State what is represented by the gradient. Hey, look at that. That would be represented as the acceleration, which is equal to gravity. The answer key says the acceleration represents the ball's acceleration, which is also the acceleration for free fall. Fancy. For the first and second, oh wait, we got to read. The man now throws the second ball with the same velocity from the same height as the first ball. The mass of the second ball is greater than that of the first ball. Assume that air resistance is still negligible, because if it wasn't, we'd have a whole different scenario. Remember when we first did this with energy? That the m's canceled out? So that would mean that the acceleration and the speeds would be the same if air resistance is negligible. So it should be the same, and it would be the same. If air resistance was not negligible, we'll do like part B, like if it were not negligible, if air resistance was not negligible, then if you have a smaller mass, if the mass is smaller the one with a smaller mass will reach terminal velocity faster or easier. And that one, if it reaches terminal velocity faster, means that it will land with a slower speed and therefore take longer. Okay? We could not compare the accelerations because the accelerations would be a sum of all forces, so that would be a little bit of a different thing. It would reach its terminal velocity faster because the sum of all forces would equal 0 quicker with the one with smaller mass. Not what the question asked, though. All right. That is going to do it for question 3.